So on the left side here, you see all of the information that we found in the last video about the function f of x is equal to 2 times x squared minus 9 in the numerator divided by x squared minus 4 in the denominator. And what we're going to do is we're going to take this information, now that we've kind of digested it here a little bit and put it into a little bit of a nicer format, we're going to fill it into this table that you see on the right hand side. In our first column we're going to put intervals and we're going to put points, and we're going to work on putting those together as we see them from left to right, same as we would on a regular number line. We're going to record information about the function, its derivative and its second derivative, and we'll also make ourselves some notes about exactly what it is that we're seeing along the way. So the first thing I'm going to do is kind of scan through the information we have here and look for the most negative value I see. And the most negative value I see is negative 3. So I'm going to let my first interval run from negative infinity to negative 3. And I'm going to note that on that interval from negative infinity to negative 3 that don't really know anything about the function, because the function is going to take on lots of different values, so I'm going to leave that blank. But the first derivative I know is going to be decreasing, because it's decreasing everywhere from negative infinity to negative 2, so I'm going to put a minus there. And the second derivative, well, it says that that's concave down from negative infinity to negative 2, so we're going to be negative there as well. And for my notes, what I'm going to do is I'm going to draw just a little segment here. Looks like that. In this case, that's a chunk of a curve that is both decreasing from left to right and happens to be concave down from left to right. If you look at your textbook, in most textbooks, they'll write out something like decreasing and concave down here. But I find that these little drawings are actually more useful when we try to graph things. Now, when we get to negative 3, something happens, and that something is we have found an x-intercept. So I'm going to write x is equal to negative 3. At negative 3, the value is 0. We know that the first derivative is still negative, the second derivative is still negative. That hasn't changed. They're going to be both negative all the way up to negative 2, and therefore we still have this shape going on. Alright, let me draw that a little bit better there. Something like that. And then we can keep doing this for intervals and points all the way down. So our next interval is going to go from negative 3 to negative 2, and then something happens at negative 2. Then we're going to have an interval from negative 2 to 0, then something happens at 0. Then an interval from 0 to 2, something happens at 2. An interval from 2 to 3, something happens at 3. And finally an interval from 3 to positive infinity. So we try to create this table so that everything is happening from left to right. So we can kind of read this table and get a feel for how the graph is changing. And then we can go through and try to fill in all the information that we have for each of these pieces. Now I think it's often easier to go through and try to get the whole table kind of set up first with the intervals and the points, and then to go through and kind of fill things out really almost one column at a time. So when x is negative 2, there is no value. This is a vertical asymptote. So I'm going to type in NA here. Doesn't make any sense. As a matter of fact, these are all going to be NA because it's a vertical asymptote. When x is equal to 0, y is 9/2. We know that is both a y-intercept and a relative minimum. When x is 2, vertical asymptote again. So none of these things apply. And when x is 3, we get back to another x-intercept. So the y value is 0. I'm going to leave the y values, the f of x's, blank whenever it's an interval, because there's nothing to write down there really unless I want to try to fill in all infinitely many values, which doesn't make a lot of sense. Now the first derivative we know is decreasing all the way up to negative 2. So decreasing to negative 3, at negative 3, and to negative 2. Nothing happens at negative 2. We know it's still decreasing from negative 2 to 0. But that exactly at 0 we picked up a y-intercept. In other words, at 0 that first derivative was 0. From 0 to 2 it's positive, and from 2 to infinity it is positive. So we can fill in the rest of those. Our concavity, f double prime of x, well, we're concave down all the way to negative 2. So we can go minus here. Then we're concave up from negative 2 to positive 2, and then we'll be concave down again from 2 to infinity. So my picture doesn't really change here. For a note here, I could write this is a vertical asymptote. On this next interval from negative 2 to 0, I need to be decreasing, but in a concave up manner. That's going to look like this. And then I get a y-intercept that also happens to be a relative minimum. Then we're increasing in concave up. That looks like this. We come across another vertical asymptote. Now in the next interval we are decreasing but concave down. It's going to look like that. Decreasing concave down looks like this. Decreasing concave down looks like this in general. So there's a table of information, and if you do enough of these, you'll actually start to get a feel for the picture of the graph right from this. But what you want to do next is go and on a graph label the vertical asymptotes, label the horizontal asymptote, which doesn't show up in this table, and then put the points on that we know, and then label the various chunks as to what kind of shape they take, and then you can start to sketch through the points that you have in each interval the kind of correct shape we have. What you're going to see following this is a GeoGebra applet, and if you move the slider, you'll be able to see how all these pieces come together and how we end up coming up with the shape of the graph. And it's all based on exactly the information that we've discovered in the previous video, and then that we've organized into our table in this video here. So this is a really good example of what curve sketching looks like. It's a long, drawn-out process, but through analysis we can learn a ton about the graph of a function without having to go to technology, without having to go to our calculators or to the internet or anything. And that's a very powerful idea and technique.